So thank you very much for taking the time on a Sunday and you're all attending this conference here. Special thanks to the organizers, sponsors, and all the other speakers for such a wonderful event today. So today's talk is on object detection to instance segmentation. Before I get there, a quick introduction about myself. I am based in Warsaw. I work for Lingaro. I'm part of the data science team in Lingaro. So Lingaro is headquartered in Warsaw. We have our offices also in Philippines and in United States. So what do we do in our company? So we build different kinds of solutions for our customers, mainly focused in harnessing the power of data for them. So whether it is building business intelligence systems or whether it is building advanced analytical capabilities or building chatbots for them or leveraging the big data platform IoT. So it's pretty much the entire spectrum. So we do a lot of projects, but the core part is on leveraging data for the customers and building advanced capabilities for them. So in the next half an hour, what are we going to be talking about is in the basically the realm of computer vision. So we are going to be focusing on the various algorithms that have gotten evolved from the fundamentals of like the object detection systems to the later ones in the instance segmentation space. So I will probably spend some more time focusing on one of the instance segmentation algorithm, which is MASK-RCNN. Because I am coming from a consulting background, so my emphasis is on, okay, how do I take the technology or all the research and the advanced developments that have happened, taking it to building solutions for the customer. So what are all the kind of scenarios can we envision? What's the value that we can bring through these solutions to our customers? So I will touch upon that as well as end with, okay, some of the challenges that we are dealing with, even after the advances in all these computer vision algorithms, when we are actually implementing it, and how some of the latest researchers are. Hopefully, they are going to solve those problems as well, and we will wrap it up with the Q&A. So it's going to be a packed next half an hour, and so this is for people who are already familiar with this. You would have seen this picture multiple times, but just to get the context for some of people who are not spending their day job or their time in the university on computer vision tasks, this just paints the picture of the various terminologies that we will be using during the next half an hour. So what is classification is something as simple as, okay, what object are we seeing in this picture, whether it's a video or whether it's a image, identifying the object that is there in the picture. So that's the classification part. Detection, or you also will see the terminology of object localization is nothing but where is this object in the image. So it's the position of the object that is seen. Here it is basically around finding the coordinates as to, okay, so this is the bounding box, this is where the object is present. Segmentation looks at it slightly differently. Here we are looking at it pixel-wise. What is the pixel-wise classification of each and every object? So does this pixel belong to a background, or does this pixel belong to an object? In this case, in this example, let's say, is this pixel belongs to a balloon or whatever it might be. Instance segmentation takes it a level further. Here, it is again pixel-wise classification, but at the same time, you are trying to identify the instances of the object separately. So in this picture, you will see multiple balloons, but each of those are actually identified as, okay, this is number 1, number 2, number 3 of this particular object. So all of this, actually, it is taking us one step towards understanding the what we are seeing. So increasing the visual interpretability of the algorithms. That's the gradual progress in all of this. And each of this will cater towards solving different kinds of problems that we have. Not like instance segmentation is needed for all of the problems. There are scenarios, it's only enough to know what the object is, where the object is. The masks are not necessarily important, but in other scenarios, you do need a much more detailed level of visual interpretation. So the family of algorithms that we will be going through in this, the first half of this session is starting from RCNN. So RCNN is the first of the several algorithms that came up, which basically identifies what are all the objects that are available. It's like finding the object proposals from the image. So it does using a separate algorithm which is not part of this architecture. So first it goes through that algorithm called selective search, finds the objects of interest, and then for each of those objects there is a separate convolution neural network layer which is trying to identify and the classifier sitting on top of it, which identifies what this object is, as well as you are trying to run it through another bounding box regressor to identify the location of the object in the image. So as you can see, if you have your selective search is configured and in a way that, let's say, it generates thousands of object proposals, you will have to run a neural network for each of those object proposals separately to finally get what you are trying to identify from the image. So obviously not the most efficient one. So the second one is fast RCNN, and the second advanced version of the model. Here, there is still the selective search, which is doing the first round of finding the object proposals. But then the convolution neural network, as opposed to RCNN, is not done for every proposal separately. The convolution neural network is run on the entire image. So basically, you're not trying to learn the same feature spaces, like all the features for a particular object of interest, which are mostly going to be overlapped. So your proposals are all overlapped in the initial phase, but that can be optimized when you are running the convolution neural network all in one go. Thereby, and on top of that, you're doing the same things again. So there is a bounding box regressor which is sitting on top of it, as well as you are trying to that's the objective of this algorithm anyways. You anyway need the classifier to work, as well as the bounding box regressor to know where the object is present in a particular image. But it's one step forward that it's definitely much faster than the RCNN. The next one, which is still relevant in many of the papers that you read now, also even in MASK-RCNN, you would find that faster RCNN still is very much used in all of these algorithms, so all of these architectures. So how does fast RCNN differ from the earlier versions? So there is no selective search algorithm which is there. So there is, which means that the first thing that happens when you train this model is the CNN is first run to extract all the features for this image, and then this network is called as a regional proposed network. How it does is, it goes through the image, and I will go about the details of it through this thing with anchor boxes which are overlaid on the features, and it trains to identify what are all the regions of interest in this particular image, and which are then again classified, and then you're finding the objects, the position of the objects. So if you look at it, there are four pieces that this network is training on. First is, there is an RPN layer, which is training on the bounding box regression, as well as there is the classifications layer, which is finding out whether there is an object in this position or not. So what the RPN does not do, RPN is not trying to actually classify the object. RPN is only trying to it's a light network, so it's not trying to understand exactly, it's not training on whether there is a particular object, like, okay, is there a cat or a dog? All that it tries to do is, what is the probability that in this area, this feature is getting mapped to an object or not? So that's what RPN does. And the bounding box regression is again not, there is not that much weightage given to this regression loss at this stage. So as long as there is enough of the bounding boxes that we are able to find, the second layer, when the actual network is finishing, the RCNN's final layer is when the classification and the regression bounding boxes are fine-tuned. So the four loss function, the loss function typically will have these four components: the RPN's classification loss, the regression loss, and the final layers classification and regression loss. Okay, YOLO is part of a different family of algorithms. It's not. It works very different than the RCNN family. So what YOLO does, another algorithm which is also focused in object detection. So it needs to identify the object as well as it needs to find the bounding boxes for the object. But YOLO does not go through object proposals at all. So it does everything in one shot. So it's like YOLO stands for you only look once. So it's not like there is first layer which finds the objects, and it's not going to classify it at the second layer. So it is all happening in one go. How it does it? So there is the input image. You can imagine an image and then having a grid overlaid on it. So there is, in this example, if you see, there is a 13 by 13 grid that the initial image is overlaid with. And each of those grid now will have to be having multiple anchor boxes. Now, anchor boxes are something like, they are basically rectangular boxes, you can say, which is some are lengthwise to identify objects which are vertically positioned, and some are on the widthwise to identify objects which are horizontally positioned, and with different aspect ratios. So you can have something which is 2:1, 1:1, which will be a square. So you have anchor boxes of multiple aspect ratios and sizes which are overlaid on each of these grid. So what you get is a bunch of grids, basically. So you will generate bounding boxes of, so 13 by 13 times 5, which is like you generate 845 bounding boxes. Not all of those boxes are going to be classified as something with an object or something with an with accurate object localized outputs. So ultimately, you will end up with 13 by 13 by 125 dimension output, where 125 is for each of those 5 anchor boxes. Each anchor box will have 25. This is for an example where you will have an object with 20 classes. If your data set has 20 classes, now all of these dimensions and everything is only with respect to a particular data set. So if your data set has 50 classes, then all of these dimensions will get updated accordingly. So the intuition that I'm trying to convey here is, after it goes through this cycle once, and the neural network is trained, you are able to identify it without going through the object proposal side multiple times. Okay. YOLO had, again, it had multiple versions as well. There is a YOLO, and there is YOLO 9000, YOLO version 3. And the two-stage detectors are the family of the fast RCNN. There is SSD is another neural network, which I have not touched upon in this talk, which is also very similar for the purpose of object detection. So if we look at how these networks have performed, the general perception is YOLO is fast, and the family of RCNNs, the faster RCNNs, are slow because of the fact that it has to go through this layer multiple times. But YOLO has not, YOLO, and the second perception is YOLO is not as accurate as the faster RCNNs, because YOLO does not deal well with object which are smaller sizes, if the aspect ratios are different, and all those sorts of challenges. Then I am exactly not sure the latest improvements in YOLO version 3, but this data, as per the paper, says that the YOLO version 3, which is with the different kinds of backbone architecture, has comparable output when it comes to accuracy with comparing with faster RCNN. So it might not. So this YOLO version 3, which comes as close to faster RCNN, might not be as fast also, because it is probably running with a much larger backbone network. Okay. So we were spending time talking about various algorithms in the object detection space. Now we will talk about algorithms in the instance segmentation. So this is, if we implement instance segmentation with any of the videos, you can find a lot of people have interest in this space, and you can find that this is how the whole instance segmentation, when you implement on your data, the output could be like this. So a quick run through with MASK-RCNN, which is one of the famous implementations for implementing instance segmentation. It basically combines two of the architectures that were already existing. The first one is the faster RCNN. So up to the time when you have to identify the object classify the object as well as finding the bounding box for the object, it is the faster RCNN in itself. They have made some modifications to it, but the fundamental architecture still remains the same. The second piece, where you are generating the mask detection, that part is actually using the fully convolutional neural network, so the FCN. So FCN, if you would have come across an FCN model, I think I'm covering it in the next section. Okay, so basically MASK-RCNN has 4 pieces of it. First is, you anyway need to understand and generate the features, so you will have to run a convolutional neural network to get all the, convert all the information in the feature space. So what network is used in the original paper is ResNet 101, but there are later implementations of it, and the open source implementation uses other networks using feature pyramid network and other networks which have constantly improved on the performance standpoint. So this is like a general idea of how, like a nice visualization, you can say, for how a convolutional neural network runs to learn the features at different levels. So you get the earlier features are just learning the edges, and then the later features learn the higher level things. So MASK-RCNN, the first piece goes through to get the neural network features generated. The second part is to generate the regional proposals. So the regional proposals are on the feature space. The anchor boxes are overlaid for different sizes, and the output is you know where the bounding boxes are, as well as the classification, whether there's an object or not. The ROI classifier and bounding box regressor. So this is where the MASK-RCNN varies from the standard faster RCNN is when the feature maps are remapped to the fixed size. So whenever you have to classify an image, one of the conditions becomes is your input becomes, there is a necessity that the input has a fixed dimension. So in order to get it to a fixed dimension, so after running the convolutional neural network, when in the feature space, each of the bounding boxes are of different sizes. The dimensions are different. So from this different size dimensions, the neural they have to be mapped to the fixed size before it goes through the classification layer. So this is where the original paper used ROI pool, which ROI pool is basically you're approximating it by not necessarily approximating. There is some kind of information loss in that. So you're only cropping off the actual downsized one, but the rest of the things information is lost, as opposed to ROI align, where there is a bilinear interpolation that is done to not to have enough to have enough accuracy when and reduce the amount of loss. So this apparently has significantly improved the performance when with the bounding box generation also. So not only for the object detection, not only for the mask generation, the ROI align has improved the performance even in the bounding box detection. So this is the last part, which is the mask branch, which works very similar to how a semantic segmentation model works. So the neural network is downsized, and then it is again upsized. I mean, basically it's upsampled, and there is a one-to-one mapping between your input and the segmentation masks that are generated. So if your class has, if you're creating the masks for 20 classes in your data set, then your output will be whatever the input dimension is with 20 equivalent outputs of that. So this is a nice visualization to understand what is happening in the semantic segmentation space. So basically, it's downsampled, and then it is again feature-wise upsampled. Okay. So from a loss function standpoint, MASK-RCNN deals with all the loss functions that the architecture trained with in the faster RCNN, plus an additional loss functions with respect to the mask, the mask head, basically. So this is again pixel-wise. You will have to map it with the ground truth and what the mask is generating, and then that's the entire loss is actually a weighted sum of all of the losses. So the reason it's a weighted sum is you want to prioritize a classification loss, like penalize the classification loss higher than the regression loss. So that's possible in this case. And or the other scenario is, let's say RCNN loss has to be much more penalized than, okay, it's okay that you miss something during the RPN, or vice versa, because if RPN does not even give you the proposals, right, then it's highly likely that RCNN has nothing to work with. So it's up to the implementation to fine-tune these aspects. Okay. So coming to the scenarios where we can apply. So it's nothing new. We all know that computer vision has impact in multiple industries. It has, whether it deals with medical imaging, sports analytics, because when the soccer season is going right now, you see so many implementations of the MASK-RCNN, wherein the player positions are detected, and then some kind of analysis getting done. So where we are trying to position it from our customer standpoint is in the field of retail space also. So we are trying to create prototypes and scenarios for planograms like how the shelf space things get organized, and different scenarios. So some of, without going like into specific details, so we look at scenarios where retail can be improved, or some kind of things in the manufacturing can be improved using any one of these techniques. So one of the points which you would notice here is human pose estimation. So MASK-RCNN actually can be changed with a slight modification to detect the human pose detection also. So there's a Facebook research paper in this where everything else that you see in this paper, in this picture, remains the same. So you have the RPN layer, you have a detection head, you have the segmentation head, which is all the same. So all that is added new is a key point head. So it's like if you are building an application for human key point detection with 16 or 17 parameters that you have, then if your data set is created for that, then there is a separate part of the architecture that has to be changed for training on those key points. There are applications with dense human pose detection and other things. Again, it's all comes under the same family of algorithms. So if we have to take this algorithm or the architecture and then go ahead and apply on our own business case or our own use cases, first thing is you need to generate data sets with those masks, which is important. So tools like Label Me, there is a VOTT, there's VIA is VGG image annotation, I think it stands for. So these are all the tools. There is a little bit of getting used to playing around with these tools to load images for your business needs or for your other papers and other things. So you will have to create the masks, and these masks are actually sometimes in JSON output, sometimes the PNG output. So, and then there are tools. If in order to use the current implementation that is out, which is open sourced, sometimes the data has to be converted into the COCO style data. So there is PyCoco tools which can be used to convert it as well. And what happens is bounding boxes is not necessarily needed from the data. So it's the masks is important because you want to augment the masks for different sizes. So you don't want to use the fixed bounding boxes and masks. Then whenever you are changing the orientation of the masks and creating other augmented data for masks, then the bounding boxes have to be generated also. So if there is a way to generate the bounding box from the masks, that is helpful. And then you have to go ahead and then go through the training and then see how it performs for your data. If data has to be pre-processed, and those sorts of things remain the same. COCO has masks only for 80 classes. So if you have objects which are very, very different than what the COCO has, and you still want to do it, then your underlying, the barebone architecture for the neural network probably has to be retrained. If your objects that you're training are very similar to what is there in COCO, then at least the barebone can be used, and the further layers have to be trained as on top of that. So a very good implementation of MASK-RCNN in this link. I will post the slide in the Slack channel after the talk. So how did I go through with this thing? I just followed whatever was there in the open source model, as well as the blog post which said how I can use it for the sample data set. So it's pretty straightforward for a basic scenario. But when we have to implement it for different kinds of images, which the positions are different, it does not fare that well. You still miss out on a lot of masks which are overlaid on top of each other. So we are still dealing with the challenges on this. So this is just an older chart for the performance comparisons. And so for people who are interested in this room for taking it further, there are very, very good implementations for this which can be used to leverage for further understanding. And okay, so latest research papers are for in this space is issues with the current MASK-RCNN works well for the objects that it is trained for. So what about the background? So if you have images like with sky and other kinds of things, it does not. So it's like in COCO there is this terminology with objects and stuff or something like that. So it's like objects. The stuff is anything which is not an object. So that is seen there. It does not deal very well with identifying that. So the paper Learning to Segment Everything is from the same authors who have done the MASK-RCNN. So we will have to try it out if data generation and mask generation challenges are dealt with better in this. And that's it from my talk. And if we have time, I could just show the code for so basically this is the open source implementation for the for the Balloon data set, which is a new data set that's derived from which is created. So all that you have to do is you'll have to create similar to this Balloon data sets. You will have to find out images for your needs, and then go through the labeling part. And after that, this if you look at the configuration, now this is all the things that we will have to play around with. One is the various aspects with the background, the non-max suppression threshold, which also changes the output differently. So what is non-max suppression is when we are identifying the region of interest, or when you are identifying bounding boxes with the objects, there are a lot of times the bounding boxes are overlapping and showing the same set of features. So non-max suppression threshold will actually remove those highly overlapped scenarios. So this is how once the data is generated and you are able to visualize on the data, this is how the visualization part of it works. And after the training, it is so this is the initial set of bounding boxes, the region of interest refinement, and finally this is how the things are generated. So if I can open up for the questions, and thank you very much.
Wow, who expected so much excitement about convolutions? Thank you. Questions?
Thanks for the interesting talk. I just have one question. In your slide in MASK-RCNN loss function, I saw that the performance of softmax lower than sigmoid. Now, to my knowledge, softmax is usually performs well on multiple object detection, at least in CNN. So I'm just curious, do you know why sigmoid could perform better in this case than softmax? Thank you.
Yeah, so I am not exactly sure, but what it's generating here, the masks are generated per class. So if I think because of the way the segmentation, the pixel-wise segmentation is happening on a per class basis, that's just my understanding, that it generates masks for every. So there are, let's say you have 20 objects at this level. It generates the masks for 20 objects separately. So when we are doing the pixel-wise mapping between the masks and the ground truth, probably the treating it as a single classification at each level, probably it's better than treating it as a multi-class thing.
Treating what into single class? Sorry.
The output masks. So considering that each of the output class is you're training the neural network to predict one of the classes at each point separately. So that probably gets the accuracy better. I have a link there. I will probably have to go and check on that why from where I took it on why exactly it is better.
Okay, thanks.
More questions?
Hi, thank you for the interesting talk. I just have a question, if you have any experience from your work on how fine-grained is this algorithm, like how can it perform on not dogs and cats and balloons, but for example, something very small I cannot think now about, but like needle or something fine-grained.
We are trying to do it, let's say, in the cartons of milk and those sorts of things. So that's the size of objects that we are dealing with. And what we are trying to do as part of this thing is we are trying to build like a pipeline, of getting the images, getting the masks, trying to leverage the existing algorithmic architecture, and then seeing how we are able to sustain with the results. So we are trying to build the pipeline now and building like a prototype for such objects. Now, whether it performs for really tiny objects or something like identifying a nucleus of a thing, right? There is a data science challenge that happens for identifying the nucleus in an image. Now, for those sorts of things, I guess we are not exactly sure. But for an object of a certain size, we are seeing that, because of the fact that they are still in the same aspect ratio and the dimension of a person standing or something, so it's still okay, but not disagreeing that for when the sizes and the dimensions changes, now the whole thing is quite a different thing altogether. Yeah.
I was wondering about, for those instance segmentation, more or less how many data you need to train on? Do you need much more data for instance segmentation than for object detection?
For specific scenarios? Or for... actually for... we are trying to generate as much data as we can for our kind of objects that we are dealing with. We are not training the backbone network, so we are still expecting that for the kind of objects that we are dealing with, we are expecting that the features can be learned even with the existing backbone. But for the objects that we are trying to ultimately classify and generate masks for, we are generating a lot of data for that. Thank you. Thank you. Thank you.